Hey y'all, welcome back. So today we're going to cap off this unit on graphing sinusoidal functions by doing a little modeling. And so what we're going to do today is we're going to look at some real-world scenarios and see how we might be able to write an equation and create a graph to model these different situations. Okay, now what's nice is a lot of things in nature do have like a periodic nature where it's a certain behavior that repeats over and over again. So that makes these sinusoidal functions very nice to use to model these scenarios. Now we are going to have to make some assumptions when working with these. For example, at least for now, most of these scenarios are going to assume that there's no friction or air resistance, which obviously is not true in the real world, but otherwise it would make these models much more complicated. So we're just doing simple harmonic motion here, assuming no friction or air resistance. But let's kind of go through these different scenarios. I think I've got 4 or 5 of them for you, and we'll go through how you can use the information in the problem to create an equation and then a graph. So let's look at this first scenario. It says consider a ball that is bobbing up and down on the end of a spring. So let's say we have a ball on the end of a spring kind of hanging from the ceiling, and say we push that ball all the way up, or alternatively pull it all the way down, and we let go and let the ball kind of bounce up and down. And so what we want to do is we want to model that behavior, or its height, or rather its displacement from equilibrium, based on the amount of time that has gone by. So this says, suppose 10 centimeters is the maximum distance that the ball moves vertically. So, so we got 10 centimeters is the maximum distance the ball moves vertically. So what we're going to use this, let's do a little highlighting here. We're going to use this number right here as our amplitude, right? Because that's the distance that it can bounce from displacement to either the max or the minimum displacement. So when I say displacement, what I'm talking about is how far away the ball is from equilibrium, from 0. So the displacement here is 10, the displacement here is 10, and to differentiate like which one's which, we'll say that if it's going below equilibrium, we'll call that negative, and if it's above, we'll call it positive displacement. Okay, so 10 centimeters, that's essentially going to be our amplitude, okay? Our vertical shift here is going to be 0 because equilibrium is at 0. The next thing to take into consideration is that the time it takes for the ball to move from its maximum displacement, so that'd be up here, down to the minimum, let me go back to where I was. So from the maximum down to the minimum, back to the maximum is 4 seconds. And so that's referring to our period. So what we're going to do is we're going to take that information and try to construct an equation out of that. So let's go through the 4 characteristics that we need to be able to graph and write an equation. So let me start writing some stuff down here. We've got our amplitude we're going to consider. Let's see, amplitude. We have to consider our period, our phase shift, and our vertical shift. And from there, we can pull out our A, B, C, and D. The form that our equation is going to take here is y equals A times. Now, deciding whether or not it's cosine or sine depends on whether or not your object starts at equilibrium or it starts at an extreme, like a maximum or minimum. So this says that assume t equals 0, so the beginning of the scenario, corresponds to the ball's maximum positive displacement. So the maximum positive displacement is where it's up here at 10 centimeters. So that means we're going to start like up here, and that indicates that we are going to use a cosine graph for this. So cosine of bx minus c plus d. This is going to just be our sort of generic format. And so what we need to do is figure out, okay, what is A? Yellow is kind of hard to see there. Is this going to be easier to see? That's a little easier to see. So we need to find A, B, C, and D. And we're going to do that by identifying these characteristics. So let's go back to the characteristics. So the amplitude here is going to be 10 centimeters, right? The distance from equilibrium to the maximum or minimum displacement is 10 centimeters. The period, it says back here, kind of wish I was able to fit all this on one slide, but it says the time it takes to go from maximum back to get maximum is 4 seconds. That's going to be our period. Okay, so 4 seconds. And, you know, I think I might throw in some units here just to have some, you know, context here. The phase shift, well, if I'm going to start my function at the maximum, then I don't need a phase shift because I'm already starting where cosine should sort of already start. So my phase shift here is going to be 0. And then my vertical shift, if I was not considering equilibrium to be 0, then I might have a vertical shift. But here, I'm just assuming that when it's at rest, my displacement is 0. So vertical shift here is 0. Okay, so let's go ahead and use all this to kind of figure out our A, B, C, and D. So let's do A equals, and we'll have one for B, and C, and D. And we'll just go through each of these characteristics and try to figure out, okay, well, how does that help us find one of the parameters? So since the amplitude is at 10, and that's the absolute value of A, we already know that we're starting at a maximum, so we know our cosine function is going to be positive. So that means our A value is going to be a positive 10. So for our period is 4 seconds. Now this is really the one that takes a little bit of work here. The way we calculate period, I'm going to show a little work here out to the side, is we say that the period is 2 pi over b. That's how we calculate period for a sinusoidal function. And what we know, we're trying to figure out what b is, but we actually do know what the period is. Right? The period here is 4 seconds. Right? Pretty sure it was 4 seconds. Yeah, there it is right there. So it's 4 seconds. So 4 equals 2 pi over b. So to solve for b, I'm going to multiply both sides by b to move this b over here, and essentially what that's going to give me, I might as well show it, 4b equals 2 pi. And then finally, to solve for b, we are going to divide both sides by 4. And so 2 divided by 4 is 1/2, so I get pi over 2. So that's my b value. I wonder if that's going to copy nicely over here. Ah, look at that, perfect. Okay, so that's my b, it's pi over 2. And then my C, my phase shift is 0, so my C value is going to be 0, and my vertical shift is 0, so D is 0 as well. All right, so I've got all my characteristics, I've got all my parameters ready to go. Now I can start filling in the numbers that I have. So I'm just going to copy and paste this, and let's fill it in with what's relevant here. So the A value is going to be 10, the B value is going to be pi over 2. And the C value is going to be 0, so there's just nothing there, and the vertical shift is also 0. So here is my equation to model the behavior of this ball on a spring. Now we can go ahead and start plotting everything. We already know all the information we need. We've already done all the analysis up here, so now it's just a matter of making sure our graph looks nice. So we're going to start at maximum, go down to equilibrium, down to the minimum, back to equilibrium. I don't know why I made this box so big. I don't really need to make it that big. But anyway, do my best here to get a little nice cosine curve. Maybe I'll start from up here. You guys know I have trouble with these graphs with the mouse. Okay, and then, yeah, this is going to continue. Okay, so there's our function. There's the graph of our function, but we still need to label all the scale. So we know this is at 0. We can see our displacement is 10, so we'll label this with 10 and negative 10. We're going to start at 0 because we don't have a phase shift, and our period is 4 seconds long. Okay, so that means this should end at 4. Now we've got enough information to put on our axes. So here's my x-axis. and here's my y-axis. And there we go. So the added challenge to these problems, they're going to be pretty much the same as what we've been doing in terms of graphing. But I think the added challenge here is obviously reading the word problem and knowing kind of how everything fits into the analysis. So being able to pick out the numbers and know what they're talking about or what they represent is really the key here. So we'll look at some more examples here, but that's really where the challenge is going to be. The rest of this should be pretty similar for all these problems. Let's move on to the next one. All right, so this next one is a pretty famous Ferris wheel problem. Not that this particular problem's famous, but just this kind of problem you'll see in pretty much every pre-calculus textbook. It's just a great scenario that perfectly models what we're trying to do here. So anyway, we've got a Ferris wheel, which if you don't know what a Ferris wheel is, it's this big ride where you get on, these are all like little buckets that you ride in, and you get on the bucket, and then it just kind of goes around and around, and it's not like a fast ride or anything, but it's usually pretty large. So what's cool about these rides is by the time you get to the top, you get a real nice view of whatever the park is that you're at. But anyway, the original Ferris wheel was constructed about, like over 100 years ago now. And it had a diameter of 250 feet. Okay, so as soon as I start getting some information here, I'm going to start labeling stuff just to kind of get an idea of what everything's going to be. So like the distance here from, let me get a different color here, from the top to the bottom, which would be the diameter, and not the ground, but the bottom of the wheel is going to be 250 feet. So this is going to be an important part of this kind of problem, is understanding that the wheel is not sitting on the ground. Okay, so there's usually going to be like a little bit of, a few feet down here that's going to kind of push, that's going to give you essentially a vertical shift. Okay, so anyway, it took 10 minutes to complete one full revolution. Okay, so hopefully you know what that is going to represent. 10 minutes is going to be our period. The lowest point on the Ferris wheel is 10 feet above the ground. Okay, this is what I was talking about earlier. So if the lowest point so in other words, like when you get on this, you're not actually on the ground, you're in this bucket, and you're actually 10 feet above the ground. So we'll just say this little distance right here is 10 feet. Okay. Write a function that describes the person's height above the ground. Okay, so we've got all the information we need to actually compute all this stuff. So so I don't have to retype every little thing. I'm gonna copy and paste some of this stuff. All the analysis here, because all that's gonna be roughly the same. All right, let me grab all this. Oops, nope, I don't wanna grab all that. Oh gosh. Can I just like undo? Undo. There we go. All right, let's see if that's enough space for what I need. Okay, so it says assume that time equals 0 corresponds to the time that the rider is at the lowest point on the ride. So here, since we're starting at a minimum, we are still going to use a cosine because we're starting at an extreme. But since we're starting at a minimum, we know that our a value is going to be negative. So let's go back, and I'm gonna erase some of this stuff. We know it's going to be negative, but we haven't really talked about what it's going to be yet. And then I will change all these numbers. Let's put a little question mark there because we're not sure. Okay, so the amplitude here, remember the amplitude is going to be the distance from equilibrium to the extreme. So if our vertical shift, or our equilibrium, is going to be like roughly right here, right halfway. So the distance between here and the top is going to be 125. Our amplitude, therefore, is going to be exactly that, 125, in this case, feet. And that gives us our a value. Since we're starting at the bottom, we're going to start with a negative cosine, so our a value should be negative 125. Now the period, it says it takes 10 minutes to go one full revolution. It's kind of a slow ride. Like I said before, these are not fast rides. So that's our period, okay? And that's what's going to help us calculate B. Okay, the period here is 10 minutes. So if the period's 10, and I solve this doing the same thing I did in the last problem, I'm going to multiply by b, and then divide everything by 10. So 2 pi divided by 10 would be pi over 5. So that's my b value. The phase shift, since I'm starting at a minimum, there should be no phase shift here. So yeah, no phase shift on this one. And we do have a vertical shift though. Like we got to think about where exactly is equilibrium. Now, if you're working this quickly, you might say, hey, it's 125, but it's actually not 125 because, as I was saying earlier, the minimum point on this Ferris wheel is not on the ground. There's an extra 10 feet there. So if I'm trying to figure out, okay, well, what is the vertical shift here? In other words, what is the distance from here all the way to the ground? It's going to be 125 plus the 10 is going to be 135. So my vertical shift is going to be 135 feet. So my phase shift is 0, and my d value here is going to be 135. Okay, so now I have everything that I need to go ahead and plot, or to create my equation first, and then I will plot the graph and give myself a little bit more space here. Well, that's probably good enough. So yeah, so my a value is going to be negative 125. My b value is pi over 5. My c value is 0, so it's just like a minus 0 here, and then plus 135. So there's my equation. Here we go. There's my equation right there, just like I had it up here. Forgot to box it. And then let's go ahead and sketch our graph. So to sketch our graph, I'm going to draw a little, I'm going to try to make this a little smaller so we can actually fit everything. That'd be nice, right? Can I grab it? There we go. All right, so here's my little 2x4 grid that I'm going to use. Do my best to make this all equidistant and nice and pretty. Okay, now time to start drawing. So we're going to start at the bottom because we start the right at the bottom. Get rid of those little blue dots on here. Okay. All right, come on. Mr. Schuler, you're overthinking this. Okay. Anyway, I really do. Yeah, so this line needs to be, does need to be a little longer. Okay, let's just make that look a little bit nicer. There we go. Okay, so we're going to start at a minimum, work our way up to a maximum, right, as you ride the wheel, and then you'll come back down on the other end, on the other side. Okay, so my graph is going to look, you know, something like this. Yeah, I don't like how that one turned out. There we go. That looks a little better. Okay, so now we're ready to start labeling everything. So we know equilibrium, we said, was at 135. Now I might just have to type these instead of trying to do it so small. So yeah, it's at 135. My maximum is going to be 135 plus 125. So you can kind of see over here on the diagram how we have the 10 feet and then the 250, which is the diameter of the wheel. So the total height should go all the way up to 260, whereas the low point on the right is going to be 10 feet above the ground. All right, the phase shift is 0, so here's 0. And then my period's 10 minutes, so it'll go all the way to 10 minutes. Oh, now since I did that in black, I'm gonna have to use a different color for my axes here. How about we go green? Okay, we haven't done green in a while. Oh, where'd my forest green go? There we go. Okay, so my y-axis is gonna be right here, just kind of where it has been on the last. Oh, come on. All right, well, it just deleted all my stuff. Oh, there we go. So there's my x-axis. I'm sorry, my y-axis. And the x-axis is going to be below, because look, here's 10, so the ground is actually down here somewhere. And there you go. So we got the equation and the graph. So that's the second one. I think I've got two more for you. Is that right? Let's see. One and yeah, I've got two more for you. So let's take one last glance at this, and then and we'll move on to the next problem. And just kind of to get ready for this next problem, I'm going to just highlight all this and copy it. And a lot of this is going to change, but at least I'll have a little bit of, I'll have something to work with, so I don't have to retype everything over again. Again, all this is going to change. So let's start here. Tiki's at a summer camp. One day, she is swinging on a rope tied to a tree branch, going back and forth over land and water. Ned starts a stopwatch when t equals 0 seconds. At that time, Tiki is at one end of her swing, 15 feet to the left of when the swing is at rest. Okay, so if I'm looking at this diagram, here's where equilibrium is, okay? And then it says that she starts over here, 15 feet to the left. So we'll call this negative 15 feet as our displacement, and so that would mean that this is going to be positive 15. Okay, come on, little mouse. All right, so we got from negative 15 to positive 15. And then it says when time is 5 seconds, she is at the other end of her swing, 15 feet to the right of when the swing's at rest. So she's at 0. She swings. It takes her 5 seconds to get. She's swinging kind of slow there. I don't know how reasonable that is, but it is what it is. So 5 seconds to get over here, and then it would take 5 seconds to get back. So our period's going to be 10 seconds. And then that's it. So now we need to write the equation and do the graph. So let's say she's going to start here. She's going to start at minimum displacement. So actually, my curve here is going to be the same. Right? It's going to be a negative cosine graph. The amplitude here is going to be 15 feet. So let's change that. So 15 feet for the amplitude. All these are going to change. I'll leave that negative, but because I know it's going to be negative. But so let's see. My A value is negative 15. Now, if this was sort of a judgment call on my part to say that this was to just sort of declare this is negative displacement and this is maximum displacement, it doesn't really matter in the sense that if you do it the other way and you start at a positive, your equation should still match your graph. We're just calling this negative because it's to the left. I think it's probably the best way to explain that. Okay, so anyway, the period here is going to be 10 seconds, okay, because it says it takes 5 seconds to get from one end to the other end. So a period gets you all the way back, so 5 plus 5 is going to be 10. So we already kind of did the calculations here with the number 10, so we know that this is going to be pi over 5. Same as the last one. Just a different unit. We're working with seconds here instead of minutes. The phase shift here is still going to be 0. And the vertical shift, okay, so the vertical shift is going to be a little different here. Vertical shift is kind of weird because she's swinging back and forth, but what we're measuring here is her displacement. So imagine this whole thing gets rotated. I'm going to try this. Oh, no, that's just going to do that. It's not going to rotate the whole thing. Oops. Okay, well, now it's just totally rotated. How do I get rid of that rotation? There we go. So, this negative 15 is going to be the minimum, and this positive 15 is going to be the maximum. So my vertical shift is going to be 0 because my equilibrium we're calling 0 displacement. So my D value is going to be 0. Okay, so D value 0. So that's going to change a couple things here. Number one, well, I'll have to go back and include that. Number one is this is going to be 0. And since my displacement is 15, we're going to go up to positive 15 and down to negative 15. We're going to start at negative 15 and go up. Now my x-axis then is definitely not going to be down here. X-axis is going to be raised up here a little bit. Right here. Yep. Oh, well, that's pretty close, but oh, it's not even horizontal. Oh boy. Oh, that's good enough. All right, so vertical shift here is 0, so we need to fix this. And and our A value is negative 15. So here you go. Here's your equation. There's the graph. I think that's all there is to this one. You know, sometimes you work through these and it kind of sneaks up on you when you're done. There's nothing more to do because we did a lot of copy and paste here. Okay, I think that's it for this one. All right, we've got one more for you. You know, just pay close attention to what we're doing here. We're trying to write the equation and then use that to graph. You know what? I just noticed one thing that I forgot here. So let me go ahead and include that. I didn't label the end of this since the period is 10 seconds and we're starting at 0. 0 plus 10 is 10. So yeah, that should be 10. 10 seconds. And then I must have forgot that up here unless I accidentally deleted it. The period up here was also 10. So let me go ahead and label that with a 10 just to have that kind of complete. All right, last one. We have a buoy that oscillates as waves go past. You can kind of see that this is going to be modeled by a sinusoidal function. It says it is noted that the buoy moves a total of 3.5 feet from its low point to its high point. Okay, so the amplitude here is going to be half that. Okay, so we're going to say that we're going to call this 0, okay, and we're going to call this what would it be? 1.75 as our like maximum displacement, and then our negative displacement would be negative 1.75. And it says it takes 10 seconds again. Oh, come on, we gotta we gotta get a little bit more creative here, but oh well. So from the low point to the high point, and then back. Oh, wait a minute. From low point to its high point. Yeah, we got a typo here. Returns to its low point. Let's fix that real quick. Low point. Yeah, because it's not going to go from low to high to high. That doesn't make any sense. Low to high to low is 10 seconds. Yeah, it's kind of throwing me off there. All right, so that means that the period is going to be 10 seconds. So let's kind of break everything down here. I'm going to take all my analysis, all my work, copy it down here, and see what happens here. All right, so let's see. Oops, don't want to grab the. Oh, come on. There's always something with this thing, isn't it? Oh, nope, don't want to grab all that. I just want to grab these. Okay, there we go. All right. Get this x-axis back where it was. Okay, so this is all work from the last problem, but I'm just going to use this as a template. Okay, so my amplitude here is going to be 1.75. Now this doesn't say where we start, but it does say it goes from its low point to, let's see, low point to its high point. Yeah, so I guess we're going to start at our low point. So, you know what, just to make things a little bit more interesting, since we did cosine on all these so far, let's say that this thing is going to start at equilibrium. So I'm going to put a little addition here. We're going to say t equals 0 represents the time when the buoy is at equilibrium and is about to move down. Okay. Yeah, I did not really proofread this before we started here. Okay, that's okay. This is just a little addition. Okay, a little extra info here. So that means that since we're going to start at equilibrium, and really that's kind of the whole point of me changing that, is so that we could use a sine function. Our sine function is going to be used when we start at equilibrium. So so let's fix all this. So instead of cosine, we're going to use sine. Okay, and I'm just going to delete all this because we don't know this is going to be all different. So the amplitude here is 1.75 feet. So let's fix our little graph here. We're going to start. Let's see, 0 is going to be our starting place. Our maximum displacement is going to be positive 1.75 feet, and our minimum is going to be negative 1.75. Okay. So we are going to start at equilibrium. So we're going to start here, and it says, well, it says now that we're about to move downward. So our graph is going to go down and then come back up and then down again. Now, with sine, usually, for our parent function anyway, our graph starts by going up to the maximum. So the fact that I have worded this so that it initially goes downward, that tells us that we're actually going to have a negative sine graph. So even though our amplitude is 1.75, our A value here will be a negative 1.75. Okay, so like this number right here will be negative 1.75. Oh, where did that go? Okay, not sure what exactly happened there, but there we go. So our A is negative 1.75. Now our period here, 10 seconds again. Gosh, I wish I would have picked a different number, but here we are. So yeah, we're going to have pi over 5b, the b value. We already calculated that 3 times already, or twice at least. The phase shift is 0, the vertical shift is 0, so that's all good. So here we go. We got everything we need, and the last thing to do, well, actually, since the period was the same, we don't actually have to change anything there. So that's it. There's our equation and our graph. I don't really think there's anything that we've missed here. And so that's it. So the whole point of this, really you want to be able to identify, what is the amplitude, what's the period, what's the phase shift, what's the vertical shift. Most of these are going to be set up to where the phase shift is 0, but it is possible that you don't start at equilibrium or an extreme, in which case you'd have to figure out what the phase shift is. You just find the distance from 0 to whatever the extreme is. I don't even think there's any like that on your homework. But anyway, that's it for today. Hope y'all are having a good day, and I'll see y'all next time.